Slow and steady progress has been the hallmark of advancement in astronomy for centuries, with each generation building instruments slightly more powerful than the last. But what if I told you there was a way to leapfrog decades, even centuries into the future? What if I told you there was a way to build a telescope that wasn't just tens or even thousands of times more powerful than what we have now, but a million times more powerful? And the best part? We don't even have to build it. It's sitting right there in the center of the solar system. It's the sun. And its massive gravitational pull can bend the path of light, turning it into a giant lens. It's already there, already built, already completed. We just have to send a spacecraft to the focal point and record the wonders of the universe that it reveals to us. Oh, yeah, and solve a host of technological and engineering hurdles, but the fun part is that those hurdles aren't impossible to overcome. The universe is right there, waiting for us. We just have to go out and claim it. I'm Paul Sutter, a cosmologist, author, and NASA advisor, and this is Near Futures. It was in 1919 when Sir Arthur Eddington finally did it. A few years prior, he had become enamored with Einstein's general theory of relativity after reading some papers based on Einstein's lectures. He was probably one of only a handful of people to understand the theory, and immediately started giving lectures on it. And there was one point he kept coming back to again and again. It was a beautiful, powerful, and complex theory, and it needed to be tested. Eddington knew that the perfect way to test Einstein's magnum opus could only come during a special time: a total solar eclipse. At those moments, when the disk of the moon perfectly blocks the body of the sun, it becomes possible to observe the positions of stars that just barely graze its outer surface. And Einstein had calculated that those stars should not appear to be where they were supposed to be. Over a century before, the astronomers Henry Cavendish and Johann Georg von Sonder, my favorite of the von Sonders, had made a crude calculation of the effect of gravity on the path of light. Assuming that light was made of tiny particles, which was in vogue at the time, they found that gravity's pull could deflect the light, sending it in new directions when it passes close to a massive object like the sun. When Einstein went to revolutionize our understanding of gravity with the general theory of relativity, he initially calculated a similar result to that of Cavendish and von Soldner. But once he finalized the theory, he had an exact solution applicable to the solar system thanks to the work of Karl Schwarzschild, the guy who accidentally discovered black holes. He discovered that general relativity predicted a deflection to be twice as strong as you would expect from Newton's theory. Einstein's result isn't best viewed as a pull of gravity. Instead, relativity teaches us that space and time are woven into a unified fabric, known appropriately enough as spacetime. Crucially, the presence of mass and energy bend this fabric of spacetime in a four-dimensional version of placing bowling balls on a stretched-out flexible fabric. I know it's hard to visualize how this works in 4 dimensions, but that's what all the heavy-duty math is for. This bending affects everything in the universe, because everything in the universe that wants to move has to move through spacetime. So any changes to spacetime affect how that stuff moves. This includes light itself. Light always follows straight lines, but straight depends on what the underlying curvature of spacetime is up to. If there's a big divot or depression in spacetime due to, say, a massive object like the sun, the light will enter that depression and get a new trajectory, based on how strong or deep that depression is. During a total solar eclipse on May 29, 1919, that's exactly what Sir Arthur Eddington was able to measure, with twin missions sent to Principe off the west coast of Africa and the city of Sobral in Brazil. The measurement was a huge success. A prediction of general relativity, completely different than what we expected from old Newtonian theory, verified through a difficult and clever experiment. The starlight that grazed the surface of the sun experienced a strong deflection, making the star appear in the wrong position. We now call this effect gravitational lensing, and it is an incredibly powerful tool in astronomy. That's because when light gets deflected, we can measure that distortion and use that to calculate the mass of the object causing the distortion. We do this all the time with the most massive gravitationally bound structures in the universe, the galaxy clusters. Just check out this image, taken with the James Webb Space Telescope. What you're seeing is light from distant galaxies filtering its way through a galaxy cluster sitting between us and those distant galaxies. All the matter in the cluster distorts and deforms the images of those background galaxies, twisting and bending them into strange, elongated shapes. This is one of our primary ways that we know that our universe is filled with dark matter, an invisible and unknown form of matter. There simply isn't enough visible matter in this cluster to make that large amount of gravitational distortion. But dark matter is a separate episode, so we'll leave that aside for now. We even use gravitational lenses to help us observe some of the most distant galaxies in the universe. Take A1703 ZD6, a galaxy billions of light years away that was discovered in 2012, long before we had the capabilities of the James Webb Space Telescope at our disposal. Before that telescope, we normally wouldn't have had the power to see a distant galaxy like that. But thanks to gravitational lensing, we got lucky. The light from that galaxy passed through a massive cluster, and the lensing effect magnified and amplified that image millions of times over, allowing us to observe it. And yes, in case you haven't noticed, I'm laying down hints that gravitational lensing is way more powerful than it has any right to be. There's nothing like your first encounter with a telescope. What it does is almost magical. You take this tube and you look through a little eyepiece, and through it the sky comes alive. The shadows and lunar craters stand in detailed relief. The great arch of the rings of Saturn swing over the planet. Distant comets and nebulas and galaxies take on shape and color and form. With a homespun telescope no more powerful than a pair of backyard binoculars, Galileo launched the scientific revolution. 400 years later, our greatest observatories like the James Webb Space Telescope peer into the deepest reaches of the cosmos. But it's not enough. There's so much of the universe that is tantalizingly just out of reach. Even our most powerful instruments struggle to bring the cosmos to us in all the detail and clarity that we desire. We cannot directly observe the first stars and galaxies. We cannot resolve the innermost regions near black holes. We cannot take a picture of the nearest exoplanets. There's so much more that we wish we could do. And so, in our unending quest to unlock the universe, we build ever larger telescopes. But we are quickly reaching the limits of our engineering ability. The next space-based observatory, dubbed the Habitable Worlds Observatory, will be larger than the James Webb, but not that much larger. And it will likely cost even more than its $10 billion price tag. And it will barely have the ability to hopefully map out the chemical compositions of a handful of nearby alien worlds. We can build far larger telescopes on the ground, like the planned 30-meter telescope that is, you guessed it, 30 meters across. But that massive instrument will stretch the limits of our engineering and still be limited by the atmosphere and light pollution. Gravitational lensing is way more powerful than it has any right to be, and it might just make it possible to leapfrog by orders of magnitude any telescope we can conceivably build in our lifetimes. To give you a sense of just how powerful it can be, we need to talk about resolution. Not resolution like for TVs or smartphones, that's nice and all. But in astronomy, this is less than useful because different objects are at different distances. If you point a telescope at the moon, you can see some features like mountains or boulders. You have a certain linear resolution when looking at the moon. But then you point your telescope at, say, Jupiter, and all you can make out are cloud bands. Your linear resolution is much, much worse because Jupiter is so far away. So to standardize everything, we instead use angular resolution. This makes the resolution a known property of the telescope, independent of what you're trying to look at. And so we can judge and compare one telescope against another in a fair way. In astronomy, we measure resolution in terms of things called arc minutes and arc seconds. This is a very old and even ancient method of dividing up the sky. And for once, we have the case where an old ancient tradition in astronomy still makes sense and describes exactly what it's trying to accomplish. To get the angular resolution, imagine drawing a circle around you. Then chop that circle up into 360 degrees. Then divide each degree into 60 sections called arc minutes, short for minutes of arc. And then divide each one of those arc minutes into 60 arc seconds. If you need even finer divisions, we'll switch to decimals because we get tired of all this divide by 60 nonsense. And if you're wondering why it's all 360 this and 60 that, you can thank the ancient Babylonians, who also gave us 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. Coincidence? Absolutely not, but that's a different episode. To give you some perspective, pun very much intended, the human eye has an angular resolution of about 1 arc minute. If you're looking at something about 1 kilometer away, you can distinguish 2 points if they're separated by at least 1/3 of a meter, which is pretty impressive. But if you hold your finger up nice and close, you can see the tiny markings of your fingerprint, which is also pretty impressive. Now let's kick things up a notch and jump right to the JWST. That instrument's primary mirror is a whopping 6.5 meters across, which is so big it couldn't even fit inside its rocket without folding up. And that gives the telescope an angular resolution around 1/10 of an arc second. So take the human eye resolution, divide it by 60 to go from arc minutes to arc seconds, then by 10 to get to 1/10 of an arc second. To give some fun examples, the JWST could see the details on a coin placed 40 kilometers away from it. Or it could pick up the pattern of a regulation soccer ball about 550 kilometers away from it. We want to go bigger, but we can all agree that the JWST was kind of a pain in the neck to make. And usually in astronomy, if you want higher resolution, you need a bigger dish. But there are ways to cheat. There is this technique called interferometry, where we place separate elements, which could be small dishes or even single radio antenna, very far apart from each other and correlate and connect the information that they get. The downside of this is that most of the incoming light hits dirt instead of dishes, so you have to work really, really hard to build up a halfway decent image. The upside to interferometry is that you get an effective resolution as if you had built a single giant dish spanning the distance between your elements. The iconic Very Large Array in New Mexico, which to me was the real star of the movie Contact, is an interferometer. There's also the Event Horizon Telescope, which placed elements all across the Earth, giving that array an effective resolution as if we had turned the entire planet into a single telescope. Whoever said you need super advanced mega engineering to do cool things in this universe? The Event Horizon Telescope has a resolution of 20 micro arc seconds. You could use it to spot a wedge of cheese sitting on the surface of the moon, but the scientists behind the telescope had slightly more useful ideas for it. Using tricks like these, astronomers have unlocked the wonders of the universe, explored the mysteries of the cosmos, blah, blah, blah. It's not good enough, especially when it comes to searches for life outside the solar system. That Habitable Worlds Observatory that I mentioned earlier, the one designed to search for life on nearby exoplanets, a super James Webb that will cost how many billions of dollars? We hope that it can generate single pixel images using the entire might of human ingenuity. And a significant fraction of our fortunes, we might get a few pictures of exoplanets that take up a single pixel. It's not good enough. Now I know what you're saying, Paul. Last time I checked, the sun is a giant ball of plasma. How could we turn it into a telescope? The answer is in gravitational lensing, which is why I spent a good chunk of the episode discussing how gravitational lensing works. Massive objects bend the path of light. Lenses, pieces of curved glass, bend the path of light. Coincidence? Yes, but it does mean that everything we know about optics we can transport over into gravity. We can create gravitational lenses, where the gravity of a massive object bends all the light that comes near it and sends it to a focal point, where you can just sit and enjoy the magnified image exactly as if a giant piece of curved glass was sitting there. Imagine replacing the sun with a piece of glass over 1 million kilometers across. This is an idea known as the Solar Gravitational Lens. What does the sun as a lens get you? Well, it gets you access to Patreon. That's patreon.com/pmsutter, where you get to support this show and keep it going. I truly appreciate all of your contributions. That's patreon.com/pmsutter. You can also use the link in the episode description below. What does it get you? It gets you a telescope with an angular resolution of 10 to the minus 10 arc seconds. That's roughly 1 million times better than the Event Horizon Telescope. And it gets you brightness amplification of up to a factor of 100 billion. I am not making these numbers up. This is the real deal, based on cold hard math and the physics of relativity. To say this is better than any known telescope is an understatement. This is better than any possible telescope that we could possibly build in any possible future for the next few hundred years, and it's literally just sitting right there. Well, almost. There are two major parts of a telescope. There are the optics, the lenses and such that magnify the image, and then there's the receiver, the output, like your eyeball or a camera sensor that needs to sit at the focal point and collect all that light. With the solar gravitational lens, we have the optics. The sun is doing the bending of light already, but we need to provide the eyeball, the sensors and detectors to capture that light, process it into useful information, and send that data back to Earth. You know me. I like to keep the show grounded, which means we need a reality check. There's a reason that we haven't actually built the solar telescope yet. Actually, there are many reasons. It's easy to talk about fanciful ideas like this, but somewhat harder to make them happen. But it's not impossible, which is why this idea excites me so much. Like I said, the good news is that the hard part of the telescope already exists. We don't have to grind a lens or polish a mirror or unfold an instrument. The gravity of the sun is doing all the work, taking stray bits of light that skim its surface and bending that light towards a focal point. The bad news is that we have to do everything else. It's easy enough to calculate where the light bent from the gravity of the sun converges at a focal point. Although it's not exactly one point, but a line. That's because light that just barely grazes the surface converges at one point, but light a little further out from that gets bent a little less, so it converges a little further away, and so on. So instead of a focal point, like you might have with a traditional telescope or your eyeglasses, you have a focal line that stretches through space. In the beginning of that line, the nearest to the sun where the gravitational lens produces an observable image is 542 AU away. That's astronomical units. If you've never encountered astronomical units before, well, that's far away. That's 542 times the distance between the Earth and the Sun. For some perspective, Pluto sits about 36 AU from the Sun. And at the time of this recording, the Voyager 1 spacecraft, humanity's most distant spacecraft, is just over 166 AU away. So completing the solar gravitational lens would require sending a spacecraft, and likely many of them, to a distance more than 3 times greater than anything we have ever achieved before. And remember, Voyager was launched nearly 50 years ago. We can't wait nearly 2 centuries for these spacecraft to reach their target. It takes a long time to get an astronomy Ph.D. as it is, and 200 years is really pushing it, let alone appetites for funding timelines. To make the solar gravitational lens work, we'll have to develop and deploy technologies to almost unimaginable distances. But before I talk about the incredible challenges we face when building this and the clever solutions some researchers have come up with, let me give you a sales pitch, just a taste of what we could accomplish. I mentioned earlier that when it comes to targeting exoplanets, planets outside our solar system, that our next generation of telescopes hope to generate single pixel images of nearby Earth-like planets. These are rocky worlds orbiting around their stars in the habitable zone, the regions where there's just enough light to maintain liquid water. These are prime candidates for finding life outside the Earth, but we need detailed, precise observations to determine if those planets are alive. The Solar Gravitational Lens has such incredible resolving and magnification power that it could target an Earth-like planet over 100 light years away and produce an image with resolution of order 1,000 kilometers. That's roughly the length of Britain, from Dunnet Head in Scotland in the north to Lizard Point in England in the south. That's a little shorter than the distance between New York and Chicago. You can learn a lot about a planet with that kind of resolution. You could build a map of its continents and oceans. You could see polar ice caps or glacial fields. You could find the rough outlines of great forests, deserts, and grasslands. You might even be able to see signs of industrialization. That kind of detailed image of an alien world would be more than enough to not only guess if life might or might not exist on it, but determine it for sure and begin to characterize it. And it wouldn't just be one planet. That 1,000 kilometer resolution is the worst case scenario. Any planet within a distance of about 100 light years is close enough for the solar gravitational lens to provide a high quality, relatively speaking, image of it with even better resolution. That includes Proxima b, a rocky planet in the habitable zone of its star, which is less than 4 light years away. At that distance, this solar telescope could provide resolution just 25 kilometers across. If there is alien life on the surface of that planet, the solar gravitational lens is almost guaranteed to find it. But 542 AU. That's a challenge, to say the least. Well, scientists have been floating mission concepts since the early 1980s. In recent years, the most detailed work has been led by Slava Turishev at NASA's Jet Propulsion Laboratory. His work was in turn funded by NASA's Innovative Advanced Concepts program. Full disclosure, I serve on the External Advisory Council for that program, so yes, there is a slight conflict of interest here, and no, I don't care. Because one, this NASA program is amazing, and two, Turashev's work is also amazing and worth talking about. The first problem is raw distance. We have to solve the primary challenge of getting hardware to a distance of 542 AU. If we were to rely on a Voyager-type spacecraft launched by chemical rockets from the surface of the Earth, it would take over a century just to reach the nearest focal point. And we can't turn to something like ion or thermal engines because those are even slower. We need to get there fast. The only thing we have on the horizon that could possibly do the job is a solar sail. This is a large membrane that almost perfectly reflects the sun's light, allowing that light to bounce off of it and generate momentum. This isn't a crazy idea, and it's already been tested in space. For example, with the Planetary Society's Light Sail demonstration mission. The nice thing about a solar sailcraft is that the sun never turns off. So even though light doesn't push things very strongly, it builds up over time, and you can eventually reach some seriously impressive velocities. Enough to cover the distance to 542 AU in only a couple decades, which means that the same people that launched the spacecraft have a good chance of getting to see the results. But the use of a solar sail opens up a couple more problems. One, we don't have a working sailcraft that can do what we need this mission to do. The other is one of mass. For a sailcraft to get a serious momentum boost, it has to be small. We're talking on the order of 10 kilograms or so max for the spacecraft, which is not a lot. I just hauled up a bag of dog food that weighed more than that. We need the optics, communication and navigation, propulsion, power source, all of it to fit in that tiny package. So to get around that, we can't just launch one spacecraft, but a swarm of them, each one carrying some piece or component of the overall mission. For example, one spacecraft could be in charge of navigation, using pulsar observations to direct the swarm's movements away from the sun. Several others could carry parts of the mirror that would then be assembled at 542 AU. Still others would handle communication relays to and from the Earth, and so on. These spacecraft would need some serious computing horsepower and a lot of autonomous systems. Once the swarm is a decent distance away, we won't be able to effectively control them. they'll be on their own, and they're going to have to solve these challenges without significant human intervention. One other downside of sailcraft is that they're hard to slow down. We have to work really hard to get a spacecraft out to a distance of 542 AU, and there isn't exactly an option to slow down and stop. Any craft would just
But
keep
what
going. But what we can take advantage of is the fact that the solar gravitational lens doesn't create a single focal point, but a focal line stretching for hundreds of AU, as different light rays from the same target converge at different distances. This is great. This means our swarm wouldn't have to slow down. They could just cruise along the line, collecting data as they go. And since the focal line is so long, they could spend decades recording observations and piecing together a final image. Speaking of that final image, that presents its own challenges. One is the nasty business of the sun itself. We will be imaging a distant target that appears in a ring right at the very outskirts of the solar surface, which is a highly active and highly bright place. We'll have to incorporate a coronagraph, a device to block out the light of the sun, into the overall instrument. Plus, we'll have to use models of the solar surface and coronas to subtract that from the final image. And that image will be huge. We're used to telescopes, where we can stick our eye on one end and see the image. That's because the magnified image of the distant target is still really, really small, small enough to fit within our eye. But the solar gravitational lens is so stinking powerful, producing such a magnificently magnified image that it's spread out through space. For example, a picture of Proxima b at the solar focal point is an image spanning over 50 kilometers on a side. Once again, the swarm comes to the rescue. The swarm would have to, swarm around the focal image, collecting data as it went. So once the spacecraft got into position, they would have to spiral as they continued moving outwards, picking up pieces of the image as they go. That's not the only maneuvering they'd have to do. If you've ever used a backyard telescope, you know that you have to track the motion of the stars across the sky. The magnified image you get is so zoomed in that if you held the telescope steady, your target would simply scoot across your field of view. Now that motion is due to the rotation of the Earth, but we generally have to account for any kind of motion in any kind of astronomical observation. A telescope at the Solar Gravitational Lens is looking at a region of space only tens of kilometers across. If it were aimed at an exoplanet, it would have to account for the motion of that planet in its solar system. If everything were lined up perfectly, and you positioned your swarm at the exact location of the focal point, you would have less than a minute before the planet moved out of view. So realigning is going to be a big issue, especially with all the power, fuel, and coordination that takes. And repositioning is going to be straight out. Each swarm will be dedicated to one and only one target. Like I said, this isn't going to be easy. There are a host of technical challenges that we have to overcome to get this kind of instrument to work. It will be perhaps the most audacious space mission that humanity has ever attempted. But in my view, to make it happen, it doesn't take generational advances in technology or engineering capacity that we won't have access to for another 1,000 years. If we put our minds to it, we could start turning the sun into a telescope tomorrow, if we felt like it. And if we're lucky enough and talented enough and committed enough, we could get results in our own lifetimes. So what do you think? Is it worth trying to build the solar gravitational lens? Do the benefits outweigh the costs? Who wants to see an exoplanet in their lifetimes? Let me know what you think in the comments, and we'll see what the future will bring.